There's a different type of compound that will become very important as we move through our discussion of chemistry, and that is what we call molecules and molecular compounds. A molecule, very simply, is two or more atoms arranged in a way that they behave as one particle. So much in the same way that a proton and an electron behave together as a hydrogen atom. Combinations of atoms can interact with each other in such a way that they become a particle, and we call these molecules. There are many millions of different types of molecules that are possible, some of which you're very familiar with. For example, oxygen, O2. An oxygen molecule is what we breathe in. It's what we use to stay alive. Hydrogen chloride, HCl. Methane, the primary component of natural gas. Propane, the primary component of propane gas. Essentially, a molecule is a small cluster of atoms that are somehow bound together. So in the case of an oxygen molecule, there are two oxygen atoms that are linked together in some way. I'm not going to talk about the nature of that linkage in this course, but you will cover it in the next. It's an electronic phenomenon. We'll leave it at that. HCl, hydrogen chloride. Two atoms that are of different elements, right? Hydrogen is one type of element. Chlorine is a different type of element. We call this a hetero, meaning different, atomic molecule. In fact, it's often referred to as a heterodiatomic molecule because there's only two atoms. This one right here, where we have the same atom from the same element, these are called homo, the same atomic molecule. Okay. This one is called methane, and it has a carbon atom, which I'll shade in a little bit to distinguish it from the hydrogens, and the hydrogen atoms are linked in a particular way around the carbon atom. So those linkages result in a molecule. So we could have another methane molecule and that molecule would be a different particle. In practice, what happens in natural gas, these molecules collide off of each other. They're bouncing around in space at very high speeds, but they're separate particles and they don't link together. This one, very similar type of idea, but now let me show you a little bit of their orientation. There's three carbon atoms now. So what I'm going to do is show the three carbon atoms first in a particular arrangement. So there's your three carbons. And then there are two hydrogens on this middle carbon, three hydrogens on this end carbon on the left, and three hydrogen atoms on this carbon on the right. There's a geometry, a shape to this molecule. That's something you'll learn in the next course. So as I said, there's millions of different types of molecular compounds out there. It's a very rich area of research and of technology and of life itself. Molecular compounds are made of these molecules, these individual particles, clusters of atoms, generally pretty small clusters. Here's an example of one. This is an ammonia molecule where you have a nitrogen atom at the center and three hydrogen atoms linked to it. Let's contrast that to an ionic compound. Ionic compounds generally don't form molecules, at least under normal circumstances, they form very large clusters of ions bound together. So sodium chloride, for example. This is a cartoon, a depiction of sodium chloride, which is an ionic compound. Table salt, right? We could imagine that if you were to drop one tiny, tiny grain of salt into water and mix it and dissolve the salt into water, this would be essentially the shape and the arrangement of the ions that are in that small grain of salt. Now, in fact, even a small grain of salt that you can see has many, many times more ions than this one has. This only has 1, 2, 3 of one type of atom, 1, 2, 3, 4 of the other in a particular row. So this is a very, very small cluster of ions. In reality, we would continue this on probably out to offside of campus, or going for a mile or so, just to be one grain of salt, one tiny grain of salt. So ionic compounds don't tend to form molecules. They tend to form these very large clusters, which we call crystals. Okay. Those are what you're more likely to observe in terms of the structure of an ionic compound as opposed to small combinations. Imagine if it were a molecular compound. You would have one sodium and one chloride bound together. That doesn't happen. They really attach to each other into these large clusters. So let's talk about these molecular compounds. Again, this is merely an introduction into them and the naming of molecular compounds. You'll go way in depth into this in the next course in Chemistry 11. So let's talk about the types of molecular compounds. The first type I'm going to talk about, and that'll be our main focus here, are what we call binary molecular compounds. And binary means two different elements. Each is a nonmetal. So not sodium chloride, not iron hydride. It would be two nonmetals. For example, oxygen with carbon, or nitrogen with phosphorus. Those are the molecular compounds that we're concerned with. Binary, just two different elements. Now, here's some examples. Water. Water would be a binary molecular compound. It's H2O, right? Hydrogen, oxygen, two elements. Ammonia, used in cleaning solutions often. NH3. Dry ice. Dry ice is really carbon dioxide in a solid form. So those are binary molecular compounds, two elements, both of them nonmetals. Note, we did have binary compounds with ionic compounds as well, but there we had ions. We had generally a metal with a nonmetal. These are two elements, both of which are nonmetals. And if you recall, the nonmetals are the elements on the right side of the periodic table, with the exception of hydrogen. Many of these binary molecular compounds are named using a system involving the Greek prefixes. So we need to memorize the Greek prefixes from your textbook, Table 2.4. The first 10 Greek prefixes are listed, and they are: 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. Naming is relatively simple using this system. If there are only two elements and both of them are nonmetals, you name the first element in its complete name. Then you name the second element, but you change the ending to IDE. So note, that's very, very similar to what we were talking about with the ionic compounds. There is an exception here, however, or not an exception, a difference. We use the prefixes to indicate the number of atoms of each element. So for example, if the formula has 3 carbons, we would look up 3 here. Tri carbon If it was the second element, that's if it's the first element in the formula. If it's the second element, then it would be tricarbide. Just change the ending to IDE. That's if it's the second element. There's some exceptions to this set of rules. We'll take a look at them. But in general, it's a very simple system for naming. There's no need to determine the charges of any ions. So let's look at some examples. Cl2O7. We look up in the periodic table and we note that these are nonmetals. In fact, I've picked elements that are all nonmetals. So be aware that when you look at formulas, you have to first determine whether the first element's a metal or not. If it is, then you need to use the ionic naming system. But if they're both nonmetals and there are only two elements, generally you use the system that we're discussing right now. Cl2O7. So let's come back to our Greek prefixes. Again, you need to memorize these prefixes. Cl2, 2 is di. O7, 7 is hepta. Okay. So what I'm going to do, first element, 2, dichlorine. Remember, the first element, you just name the element. Second element, but use the prefix. 7 is hepta. Hepta oxide. Now, you will find in the literature that sometimes people will drop the A. So I'll circle it here and call it hept oxide. And that's perfectly fine if you do it that way, as far as I'm concerned, or you could call it hepta oxide. Let's take a look at the second one. Again, these are nonmetals. Disulfur, difluoride. Okay. Third one, 2 nitrogens, so dinitrogen. Five oxygen, pent or penta oxide. 4 phosphoruses, 10 oxygens. 4 is tetra, so tetra phosphorus. 10 is deca, so either deca oxide or decoxide. I'll write it in there. It's up to you whether you want to leave that A in. If there's only one atom in the first element, do not use mono. So we wouldn't call this monosulfur. There's no reason to put the mono on if there's only one. We'll just call it sulfur. So SO2 would be sulfur. And then there are 2 oxygens, so dioxide. 1 carbon, 2 oxygens. 1 carbon, so carbon. Dioxide. PF3, 1 phosphorus, so just phosphorus, not monophosphorus. Trifluoride. Now, there's a couple of details in here that we should also be aware of, is that if we have 1 oxygen, or 1 atom of the second element, we do use the mono. So it's only if there's 1 in the first element we don't use mono, but if there's 1 in the second element we do. So this would be carbon. And this would be monoxide. You might want to write monoxide, but there is the convention that we don't put monoxide. We simplify it to just monoxide. So whereas there's a little flexibility, decaoxide or pentaoxide or just decoxide or pentoxide. For the second element, if it's 2 O's in a row, we don't want to say monoxide or monoxide. We drop one of the O's and call it monoxide. So we do use the mono for the second element, but we don't put 2 O's together. Now, there are some compounds, some molecular compounds, that we do not use this naming system. In fact, there's most compounds we don't use this naming system. There's some common materials we should be aware of. For example, H2O. We might be tempted to call this, based on our system, dihydrogen monoxide. Don't call it dihydrogen monoxide, just call it water. NH3, you might be tempted to call that nitrogen trihydride. Nope, just call it ammonia. These are common materials. Now this one I don't expect you to know, but this one is called phosphine. So be aware there are compounds that, even though they look like you should use their systematic naming system, they actually have what we call common names. These are called common names. They're historical names. And that's what we use for them. So water, ammonia, you should definitely know these formulas and their two names. This one, not as common. Okay, so that pretty much wraps up our discussion of that. We do have some other different types of molecular compounds, but for right now, focus on the naming system that we just discussed using the Greek system, because that's the one you really want to focus on. It's the one you want to be good at, being able to name it. So work on this system, use the textbook example problems and the end of chapter problems that are in the syllabus to work on that. And of course you'll get some practice with it on an ALEKS, but do as many of these problems as you can. And that pretty much ends what we need to work on for this section and for this chapter.